All right. So quick roll call one more time. So we have Dave, Praneeth, we have Chris, we have new Chris, we have Neil, Ojas, Prisha, Rehan, Sarah, Sivatsav, Sunarka, and Rehan. Let's get started. So did any of you get a chance to see what are the topics that we are going to cover today? No? Okay. So then I will just read it for you guys so that we are on the same page when we start. So what we are going to cover essentially at a high level today is we are trying to cover or complete Unit 2 so that we can start Unit 3 from tomorrow. So when we talk about Unit 2, we'll still talk about some parts of the data representation that we talked about. We talked about pie chart, bar chart in the last class. We'll just cover histogram, and then we'll talk about scatter plots and some of the behaviors of scatter plots. Then we'll talk about linear and exponential growth, and we'll touch upon the basics of probability, and then we'll talk about data inferences and margin of error. Okay, so I talked about a lot of topics, but you don't have to memorize them all. We'll go through the concepts, and then we will see how much we are able to cover today. Hello, Sravya.
Hi, sir.
So yeah, I was just telling what all we are going to cover. So let me not repeat myself. Let's go through the topics one more time. So again, at a high level, our plan is to cover all the remaining concepts of Unit 2 so that we can start from you can start Unit 3 from tomorrow. Okay, so let's start with where we left in the last class. Everybody can hear me okay, right? You guys can see the board as well? Okay, cool. And just an announcement for you guys that I do monthly test, and when I say monthly, I'm not being very disciplined. We are not doing every 4 weeks because 4 weeks goes by very quickly. So maybe every 6 weeks at a high level. So I'm planning to take one test in the month of February. So we have just 2 more weeks to go. So we'll plan one of the class as a test. And again, when we do the test, it's not for gauging any of you. It's more to gauge my way of teaching. Am I being effective as a teacher? Am I covering the things properly or not? Am I able to explain the concepts to you guys or not? Hi, Anshu. Okay.
Hi.
So we will probably have one test towards end of this month. That's what I'm thinking. Worst case scenario, we might end up doing the first week of March. But any which way, we'll have one test coming up soon. Not for you guys to get stressed out. It will be more of a reflection of what we have learned and how well we are able to use that 1 hour window for doing SAT during the actual exam. So it becomes more like a mock preparation or mock test of what you guys will actually come through or go through when you do the SAT test. Okay, so let's start. So today we will focus on the remaining concepts of Unit 2. We'll talk about some of the other tools for data representation that we covered in the previous class, and then we'll talk about probability, and then we'll talk about data inferences and margin of error. Now we talked about pie chart, we talked about bar chart, things like this, and I'm assuming that you guys have a fair understanding by now with respect to what these tools are used for. It's again, these are more visual representation of data for people so that they can look at the data without reading too much of content. They can make a decision out of it. Let's say if you want to relate this with one of the most practical example, let's look at this data which is more like representing. I mean, if you just want to relate to this one, all of you would have seen, hey the mystery, all of you would have seen the reports that were published during the COVID days, right? Month on month, by state, by country. It used to say, let's say, if this is representing the COVID number of new COVID cases every week for Texas, and every 1 unit is representing, let's say, 1,000. So this is week 1. 1,000, 2,000, 3,000, 4,000, 5,000, and then let's say week 1 had 4,300 new cases found. Week 2 had let's say 4,000 new cases. Week 3 had 6,000 new cases. So when somebody looks at this data as a COVID data, say, oh, between week 1 and week 2 there was still things were settling down, but all of a sudden there was a spike. Maybe because of a new variant found. Maybe because our medical system was not able to react to things in a much quicker way. So then people would draw inferences from this data, say, okay, fine. So there was a spike. Was it because of new variant, or was it because of the medical system not responding appropriately? So when the hospitals look at it, they'll have to say, okay, fine. I see there's a spike. That means we have to build more capacity. We have to have more staff. We have to have more beds in the hospital. So that solves the purpose. Is that making sense so far? Okay. Now so this is called bar chart. Just because you see those bars, right? I mean, I don't know if you guys have heard about Cadbury's dairy milk bar. You might have. During my childhood days, those were a big thing. So since these all look like big or small size bars standing one after another, representing something, that's why it was called bar chart. This looks more like a pie. Let's say if I say 100 students in the class, 30% liking science, 20% liking math, other 30% or 35% liking social studies, and then 65 plus 25 and 15% liking arts. So how the whole pie is distributed among 4 categories of students. So it represents that distribution. It represents the correlation between the data. Say, okay, fine. If you look at this data, if you compare math with arts, you clearly, by looking at the graph, the pie chart itself, you can figure out, oh, there are more students liking math compared to arts. Other interpretation that you can draw from this is, okay, the maximum percentage of students liking social studies, maximum percentage of students is liking social studies, and science is giving a close competition to that, right? So that's how, when you look at this data in a more pictorial form, it gives you the ability to make a decision much quickly compared to reading a paragraph to derive a conclusion out of it. Yeah. So these are some of the tools that we talked about. Let's look at another tool that is called histogram. Who in this class has not heard about this tool? What is a histogram and what is a bar chart? I mean, what bar chart you all saw. What is the difference between histogram and a bar chart? Any guesses?
A histogram is a range of values.
It's a range of values, okay. Bar chart is not. Bar chart is representing certain occurrences, right? I mean, like if you say 2001 data, 2002 data, 2003 data, these are absolute values or absolute reference frame against which you are trying to compare. So let's look at a histogram in a more realistic term. And one thing that you guys will probably kind of get bored of me or get tired of me would be everything relates back to teacher and student, right? I mean, for me, that's the most relevant thing to talk about when I'm interacting with you guys. So let's say in a class, we pick up a score of 10 kids. One kid got 30%, 30 marks out of 50, let's say. So this was the total number of marks that anybody could score. One got 30, second one got 35, third one got, let's say 45, fourth one got 42, fifth one got 18, sixth one got 25, seventh one got 30. Okay, so I'm trying to rush through this a little fast. So now, when I have this data, right, then there are 3 more kids, okay? I'm just making it up right now, whatever it be. If I want to represent this, the absolute value, whether it's 42 or 45, doesn't really make much of a difference to somebody like me as a teacher. For me, this guy did the best, this guy is very close. So it doesn't make much of a difference for me. What do I mean by that? If I keep these two in the same bucket, in the same group of students, both are good students for me. Because they got good percentage out of 50. Alright? I mean, they scored well against their total marks. What matters the most to me is this. This is where I have to spend a little more time with the student to see where the gap is. Yeah? Or this defines the average for me. That yeah, these are the good kids who are doing good. So basically from this I am trying to derive some trend where I am trying to group them into different categories. Okay, these are average students, these are very bright ones, or these are the ones who have done very well, and these are the ones who were probably missing some concepts. So if I group them into different categories, that helps me actionize that, say okay fine, I would focus more on this group of kids who need a little more support. I would probably put a little less focus on the kids who are doing average, but I have to find out ways to enthuse them so that they can do better. And then with these guys, they are doing well by themselves. If I just make sure that they stay focused and they continue with their current momentum, they'll continue doing good. So that my overall class does good. So what I would do is, I'll set 3 categories. Okay, I'll put one category as 0 to let's say 25. This is my one category. Then 25 to let's say 40 or 38 is my second category, and 38 to 50 is my third category. So these are my bright ones. Let's say out of 10 kids, 3 kids got 1, 2, 3, 4, 5. Okay, so 3 kids got more than 38, less than 50. Let's say 6 kids got, or 5 kids got 1, 2, 3, 4, 5. 5 kids got 20, between 25 and 38. And I see one. Let me make it up, saying that okay, this is 5 plus 3, 8. So 2 kids got less than 25, which is a matter of concern for me as a teacher. So what you will see here with the histogram is, this is a range, like Ojas said. This is always a range. You are not looking at absolute value. I did not say, okay, how many kids got 25. I said, how many kids got scored in this range. So this is always a range, and you will find them as contiguous range that you talk about. So that you'll be able to determine that okay, in this range how many kids got what, in this range how many kids got in this range how many kids were there, and this range how many kids were there. So that gives me 3 different action items for these 3 group of kids. Am I reaching everybody? Yeah? Is everybody able to follow me? Sunarka, Rehan, Shravya, Dhanushree, everybody? Srivatsam?
Yes.
Okay.
Yes.
I'm just randomly calling out some names, okay? No other hidden mischievous intent, okay? And I might call same name couple of times. I might call some names alternately, and I might miss to call some name, but it's just a random exercise. Just I'm trying to make sure that everybody is with me, okay? So the primary difference that you would see between a bar chart and a histogram is always a range against which you put your graph. Bar chart is absolute thing, be it for year, be it for month, be it for weeks, be it for days. Your reference against which you are trying to plot, that's an absolute value. While histogram has a range. Yep. So I'm kind of repeating myself multiple times just because to enforce the fact that bar chart and histogram are two tools that you use for data representation, but there's a very thin line between the two. Unless you know that one is a range, one is absolute value, you might get tempted to choose one of them, and that's where you might go wrong. Or another way to look at it is, if you have histogram, you will have contiguous thing. You will not say 0 to 25 and then a break here and then say okay 26 to 38. You will have everything contiguous. Whether that range has value or not, that depends on the data that you're dealing with. Yeah. Alright, so we looked at pie chart, bar chart, histogram. Now there's one more thing called scatter plots. And that's another tool. I mean, nothing very unique about it. It's just another tool where the representation style is different. Let's say you're talking about huge volume of data. Okay, I mean, let's say again same thing. Let me pick up a case where I say, okay, so let's look up think of a scenario where I'm talking about growth of a child with age. Okay, so I'm saying or height of child with age. So on the vertical axis I will put height. Okay, so let's say 5 years, 10 years, or no, let me put height here. 3 feet, 4 feet, 5 feet, 6 feet, 7 feet. Okay, I have not seen many people with that height, but let it be. Now I'll say 2 years, 4 years, 6 years, 8 years, 10 years, 12 years, 14 years. And I'm cooking up something on the fly. You guys can always, or you will come across different scenarios when you're dealing with it. Now, let's say we collected data for 100 kids, okay? And we found that with 2 years, one kid was 3 feet, another kid was 2.5, 3.5, some was 4 feet also. I mean, you would have not seen 4 feet tall kid at the age of 2. So let's say, okay, I'm not explaining it much. Let me put the data and then let the data talk about it. Okay, now when you see it on the board, what does it mean? The way data is represented is on the horizontal axis or the x-axis I have age, and on the vertical axis I have height, and every dot that you see here is representing one child or one child's age and the corresponding height. Okay, so if you look at this data here, let's say there were 50 kids data that we have picked up and we have plotted it, and you will always see, okay, so you'll always see that when you're looking at similar data, you're looking at age of kids. When I say kids, obviously I'm talking about human kids, right? So you will see that there is a certain pattern that depicts how generally the height will grow on average, right? There will be some outliers, the dots that you see here versus here versus here versus here. What do you mean? What does it mean? There are some kids who are 1.5 feet tall at the age of 6. That is because of some medical reasons. There are some kids who are super tall at the age of 6. Obviously, you'll not see somebody being 7.5 feet tall at the age of 6, but just for the sake of maths, let there be one scenario. Because data is something, that data is data. I mean, we don't have any way to influence it. We just selected the data and we have plotted it here. So basically, when you see your data being represented in this form, this is called scatter plot, where you have all your data scattered all across or plotted on a coordinate plane. This is called scatter plot. And these data that you see, these are the outliers. These are very rarely occurring scenarios. This is not a very normal thing, right? You'll not see probably a 16, 17-year-old kid who is just 4 feet tall. There's certainly a medical reason for it. Yeah? So, where you have the mass or the majority of the data, which determines the trend, if you try drawing a line which just goes through this is called the line of best fit. This derives the trend. This tells you that this is on average, any child at the age of 2 will be probably 1 foot tall. When at the age of 4, most of the kids are around 3 feet tall. At the age of 6, you will see most of the kids are close to being 4 feet tall. By the age of 8, they are 4 feet few inches. By the time they are 10, they are about to hit 5 feet. By the age of 14, maybe they'll be like 6 feet. I wish I was that tall, but yeah. I mean, this is just again data, right? So, this is called line of best fit, which is nothing but a consolidated view of this. Or in mathematical terms, you can think that, okay, this is the law of averages. So, this line is defining your trend or the law of averages with the data that you are looking at. And that's why it's called line of best fit. Obviously, you don't want to deal with this data as one point to derive a trend. You don't want to deal with this data to derive a trend. You would look at all the data which is probably covering 90% of the information, get the average of that and come out with the average which will give you the line of best fit. You don't have to do all that calculation as part of your exercise. This, by looking at this data, the concentration of data, you put a line which just crosses through that, and you will see data being more or less uniformly scattered around that. So this is called scattered plot, and this line we call as line of best fit. Let me take a pause here. Try to understand if anybody has any doubt with respect to whatever I have mentioned so far. Any doubt, any confusion, anything that I am troubling you guys with? Neil, Sarah, Vihan?
Answer.
Everybody's fine? Okay. Yes, Chris, go ahead.
Wait, could you explain how do you find the average of a scatter plot again?
So, as part of this exercise, you don't find the average, okay? What you do is you plot the information, and then with some guesstimate you try drawing a line which kind of passes through that, okay? So there is no tricky calculation involved here. It is just more of a more of an intuitive derivation from the data. You have plotted all the data, right? Let's say you have plotted all the data. This is your scatter plot right now, okay? Now, if you have to find out your line of best fit, what is the intent of doing that? Line of best fit is something which is going to derive your approximate mean of the whole thing, or which will give you the trend. Would your line of best fit be like here? No, right? So this doesn't look like a line of best fit. So you will say, no, this is not the one. Would your line of best fit be here? No, right? Your line of best fit has to go through or be very close to majority of the data that you are looking at. If you put a line of best fit here, this looks closer, but still it's only covering, intuitively if you look at it, right, this is probably covering only 10 to 15% of the data. Rest 80% is above this. So to make it more appropriate or more relevant, you'll say, okay, fine, let me pick up something which covers major part of it, and that is how you derive that. Otherwise, there is no science to it. There is no mathematical way to find it out. You have your ways to find out the average. You have your ways to find out mean, median, mode, right? So you will use those techniques. Here, when it comes to scatter plots, it's more of a intuitive derivation of what is the line, what is that curve, what is that diagram which tells you that this guy is probably touching major part of it, and everything else around it is symmetric to this, right? I mean, if you put a line of symmetry here, you see that the number of data that you have above this versus number of data that you have below this looks pretty much, similar optically. Yeah. Chris, did I answer your question?
Yes, sir, that was good. Thank you.
Okay. Yes, Dave.
So I have a question. Would the line of best fit always be linear, or could it be like, for example, a square root function?
So mostly with respect to scatter plots, line of best fit, right? When you are saying line of best fit, you are basically saying a line which is covering majority of the data. But imagine if you have your data, let's say here and here, you have a lot of data. So you will not make an attempt to see when you are covering majority of it. Then when you try drawing something like this, that is when it doesn't remain linear and it is still a line of best fit. Okay, so line of best fit has to be a line. It cannot be a graph, a curve, or something which is more of a polynomial. So if your data is scattered this way, you still have to find out something which passes through the center of it, so that your data is more symmetric against this line. If you have equal number of records here, equal number of data points here as well, then you will put something in the middle which says that okay, majority data is crossing this, and the number of data points that you have below this versus the number of data points you have above this are somewhat close. So it's more of an intuitive derivation rather than any scientific derivation of this whole thing. Yeah?
Thank you, sir.
Okay. Alright. So this is the line of best fit. Now, whenever you talk about line, what does come to mind? My line, which is here versus here versus here versus here, they have different meaning. Correct? And one thing that by looking at the line you relate is, oh, this has less slope, this has more slope, this has even higher slope, this is going the negative direction. Or slope part is clear, right? This has less slope, more slope, much more is going in the negative direction. How do you interpret that? Let's say if my line of best fit is this. How would I read this information? Meaning the slope is less. When I say slope is less, meaning my value of y is changing very little with every change of x. Correct? Meaning, now look at this, okay? Let me give you guys some example. Let's say you look at this line of best fit as for Africa, okay? And again, I'm not trying to say anything disrespectful to any country, okay? Or let me say this is country A, this is country B, this is country C, this is country D, okay? So we plotted 4 scatter plots for 4 different countries, okay? Data from 4 different countries for the kids, and we plotted these, identified those lines of best fit. When you look at these 4 lines of best fit, what does it mean? Let's say country A, line of best fit has less slope. Meaning, how would you interpret this information? Oh, with increase of x, y is changing very little. So for every increase of x, y is changing very little. Meaning, country A, slope is less. Meaning, value of y is changing very little. Meaning, height is increasing very little with the change of age. That means, there could be a case of malnutrition. There could be some biological reasons. There could be some genetic reasons as well. So, this scatter plot, which looks very innocent as a graph, more like a game that kids play, but there is a lot of hidden information in that. If you look at now this is country B, where with increase of age, height is increasing, but not increasing much. An average height, which is the maximum height till the growing age, is only 4 feet. That's still a matter of concern. It could be because of a number of reasons. This looks like your average, where it's growing decently. Now this also looks a problem, where when somebody at the age of 4 years is 5 feet tall, and if this is a trend of a country D, there's a problem in country D, right? You would need much taller houses actually, right? Your teacher is only 5 feet 7 inches. I can accommodate in any house. Imagine if I was 7 feet 5 inches. What would I have done? What would have happened? I would have needed a much bigger house because otherwise I would have banged my head every time I entered the door. So there are a lot of things that relates to this data to derive some interpretation from it. There could be medical reasons for kids growing that fast, which is looking very unreasonable, unrealistic. So basically what I'm trying to say here is, when you look at the data, when you plot the data, when you try deriving interpretation from that, there are a lot of messages, lot of indirect messages or inferences that will be drawn from the data. That was one of the topics that we wanted to cover. So just by looking at the graph that you saw, the pie chart, the bar chart, the histogram, and now the scatter plot that you're seeing, there are a lot of inferences that we are able to derive from this. Yeah. So the line of best fit, which was looking like just a poor line, that has a lot of hidden messages. When it's a line, every line has a slope. And when you say slope, you're talking about how it's growing against this parameter. I mean, how this is growing against this. Now if you look at this one, this is a negative one, meaning when your age is decreasing, going to -2, -4, obviously there is nobody with negative age, but from a data point of view, when it's decreasing, then why is increasing? Meaning if somebody has a higher height at a lesser age, when the age is increasing from more positive to less positive, height is decreasing. And that's a matter of concern, right? I'm already not tall enough. Imagine a situation when my height starts decreasing further. At the age of 48, I am 5'7", and by the time I turn 52, I become 4'9". That's a big problem. And that will be because of multiple reasons. So look at the data, and from that data we have to understand it, interpret it, and draw some inferences from it. That's the sole purpose of each and every data representation tool that we talk about. Be it line graph, be it histogram, be it bar chart, pie chart, scatter plots, and there is one called line graph also, which we have not talked about yet. We'll cover that. But so far, whatever we have covered, is it making any relatable sense to you guys? You should not be learning math just because you have to score good in the exam. Are you able to relate to what I'm saying? Okay.
Yeah.
Okay, good. Now, there's one more form of data representation that's called line graph. When you guys are as lazy as I am, you have one more option, and to represent your data. Let's take the same example of the temperature of 7 days in a week. Okay. So this is Monday, this is Tuesday, this is Wednesday, this is Thursday, this is Friday, this is Saturday, and this is Sunday. So I always have the option, okay, let's say this is 30 degrees, 50 degrees, 70 degrees, and I'm talking Fahrenheit, okay? 80 degrees, 90 degrees. So I always have the option of plotting a bar graph. Okay, Monday was 85, Tuesday was 79. Fine, and I can go on doing it for the rest of the days. Now, if you are doing that, I have another option that I'll see how to find. Monday was 80 degree, so here. Tuesday became 75 due to some rain. Wednesday became, it again picked up and went to 83. Thursday remained at 33. Friday went to 89. Saturday was a bit relief, came down to 80 again. And Sunday stayed at 75. Now, instead of plotting a bar, that was a little tiring for me. I just identified those points or the temperature for respective days, and then I just joined these. This is called line graph. Now, by looking at this also, we get a lot of insight from this data. You see, when you see a dip, oh, this is decreasing. So from Monday to Tuesday, temperature decreased by 5 degrees. It increased by another 7-8 degrees and then stayed stable for one more day before it increased again on Friday. And then Saturday got a little cooler because of snowfall in some other region or due to the wind, and it kept on dipping for remaining 2 days and stayed stable around 70 degrees by Sunday. So just by looking at this graph, I was able to frame a story with 5-6 sentences. That is the purpose of these graphs. Think of a scenario where, or any chart or any tool, data representation tool that you talk about. If somebody has to put a story and then plot a graph, that is the idea. But this guy goes, or any other tool goes the other way around. You have a graph, it gives you enough content, enough meat to create your own story the way you want to create. Yeah? And it is meant to be intuitive. If it is not, then we have not chosen the right tool, or we are not plotting or we are not organizing or massaging the data before we put it on a tool. And these are called tools for data representation. Any questions? Sunarka, any questions, brother?
No, sir.
Alright. See what's up? Very quiet? All good?
Yes, sir.
Okay. I know some of the kids are not well because of the ongoing flu. I'm hoping that all of you are staying safe and staying away from illness. Do your best. Now, so we have looked at some of the most commonly used tools or the data representation techniques. And again, we started our journey with the fact that you have data, and data, trust me, data keeps on growing. Even if I don't grow further, I am sure I will not grow. But data doesn't stay like me. Data keeps on growing. So that's one of the information for you guys. Now, with everybody using data, right? We use data on our phone. Walmart uses the purchase history data, product data, whatnot, right? Every information is called data. Now data everywhere is becoming huge, and that's why data scientist or data analytics is becoming one of the hot job opportunity area also. So I mean, in my days of when I was trying to figure out which career to go for and all, it was medical engineering, public services and all those things. Now, at that time we had no clue about what exactly could be around data. We were all talking about developing applications or building some tools. Now, nobody talks about it. Everybody talks about how do you look at the data to make decisions. And that's what all these data representation tools and techniques enable us to do. And obviously there's a lot that happens in the background. We are talking about record of 10 students. Think about data analysts dealing with millions of records, millions of data, right? And then doing some slicing, dicing of data and doing something about it. So yeah, at your age, you don't have to worry that much about it. But what I'm saying is, this is a very important thing because this gives you much more power with respect to decision making. Not only you and me, but everybody who looks at this information. Yeah? Shall we move on? Do I scare you guys? Have I ever scared you guys? No, right? Hopefully not. So if I'm not scaring you guys, then my request to you all would be, I mean, don't treat me like a friend. I cannot be a friend. You guys are almost 1/4 of my age. But at least be open, be transparent and share. Okay? There are a lot of things that you guys will learn, and that learning grows by a few folds if you share. So share with me, share the question that you come across, any problem that you're trying to solve, that you're taking time. Share with me, share in this group also. Trust me, this group, I mean, we can do wonders as a group. Okay, so any interesting question, any problem that you come across, please don't hesitate to share. It's okay, nobody is going to make an impression out of it. If you're not going to solve a problem, that's not a crime. Share, and you will see that once you share a question in the group, say, okay, this one I am trying to solve, you will find 5 different ways to solve that problem by 5 people responding to it. And you will always have the option to choose the best or the most impressive among all. Because ultimately your objective is to, when you go for exam, you want to make sure that you solve any and every problem in the most efficient way, in the least possible time, and without going wrong or possibility of being wrong. Correct? So okay. So let's look at few problems. Okay. So we have covered the main concepts that we wanted to cover. And we can start we can start unit 3 from tomorrow. But let's look at some questions that that I wanted to kind of quickly run through with you guys. Okay. Now there's a question. Okay. Since you guys haven't got a chance to look at it, and this is all about data. Okay. There's nothing fancy about it. Okay. So it says, I will not write so much of English. Let's say color. Large, small, and total. Let me put it here first. We have red. There is no information given here. It says 4, and then this is also kept blank. This is blue, 5, blank and blank, and then this is total. Here there is a blank, here there is a blank, there is 24. So this is the information that is given in the question. Okay, let me read it for you guys first, which I had shared. And again, the reason why I picked up a question, because what happens is after explaining the concepts, if I have to pick up a right question, sometimes I make it up, and if I don't pick the right level of the question, then you guys will get bored or tired. So let me read it for you guys. Margot classified her favorite paintings hanging in a museum by both size, dominant color. So somebody named Margot classified her favorite paintings hanging in a museum by both size and color. So that's why you see color on this dimension and size on this dimension. Okay. Now the results are in the table above. This is a table. Margot found that 1/4 of her favorite large painting were blue. 1/4 of her large painting were blue. Okay, so that's the first sentence. Margot found that 1/4 of her favorite large paintings were blue. Favorite large paintings were blue. So I'm just writing it here. Okay, 1/4 of favorite large paintings were blue. Okay. How many of Margot's favorite paintings have red as the dominant color? So see, you have this table. It says that this table has information about the paintings that the person Margot had in that exhibition, whatever it was, which were every color paintings were large and small in size. Red color painting were some were large, 4 were small. Total we can figure out. Blue color paintings were 4 in large size. We don't know about the small one. We don't know the total. And if you look at this total is sum of large plus sum of small, which is 24. Now the other information we have got is blue were 1/4 of her favorite large paintings. So whatever is the count of blue, that was 1/4 of her favorite large painting. So let's say the number of large paintings were X. So it says that blue by X, okay, whatever was the value of blue, which is 5. 5 by X equal to 1/4. So now what we are saying, what is the total number of large paintings, okay, and blue was 1/4 of that. So from that, the total number of large paintings were how many? 20, yeah. So that is blue by total. So by X is total. So blue by total is 1/4. Blue is 1/4 of the total. So that is X gives me 5 into 4, which is 20. So now we know this total is 20. Now, see, let's start filling the blanks here. David, you are 12 minutes early in the class. Okay, so this is 20 and this total is 24. So what is missing here is 4. Now, when you know this is 4, small 4 plus something is 4. So this means this one is 0. Okay. Now, 5 plus some 0 will be nothing but 5. Now, something plus 5 is giving me 20. So this is 15. 15 plus 4 is 19. So now we know everything here. We know that total number of red paintings were 15 and blue were 5. That is how blue was 1/4 of all the large paintings. And you can just add them all and see if we have made any mistake. So in this whole thing, when we were looking at the paragraph, it was looking a little tricky. But after we read that and found the clue, this was the clue. Blue is 1/4 of my total large paintings. And you had the information for blue. As soon as you determined what was the total number of this, everything else was just filling the blanks. Yeah. So this was one of the examples. Again, you will say, what is the relevance of this one? This was actually a probability problem that you guys solved without knowing about it, right? And probability, if you look at probability as a concept, I mean, obviously we'll go deeper into it. As part of this unit, we are just covering the tip of the iceberg. We are only just talking about the foundation of probability, where based on certain information, you are deriving the possibility of an outcome. And the information was this: blue is 1/4. Based on that, you could find out what is the probable value of this, and rest all was you are able to relate. Yeah. So if you look at, see, we did not cover probability as a concept, but let's look at one simple example. Okay. If I say that I have 2 red chocolates or candies, whatever, in every 5 candies. So basically, I have 2 red candies in every 5 candies. How many red candies I will have, or I can have with 100 candies? This is again a relatable probability scenario. You know that the probability of 2 red candies, red candies probability is 2 out of 5. 2 out of 5, how many out of 100? And this is just, you can just relate and find it out. Yeah. So I'm not going deeper into it because we'll cover probability in more depth in the subsequent units. But probability at a concept level, if you talk about, is nothing but the likelihood of something happening based on some mathematical relationship. That is what would be our starting point when it comes to probability. So far, whatever we have covered, any doubt, anything that is not going down well, let me know. No? This is when I get little confused. If I don't hear a response, what should be my reaction? What happened? Prishan and Sue, you two have the reputation of being the first one to react. What happened? You guys also quiet today? Anything that is not clear with her? Sunarka, Praneet?
No, sir.
No? Okay. You don't sound right. I'm hoping that you are getting better. Now, let's look at one more concept before I let you guys go. It's called linear and exponential growth. And again, there are a lot of things that we will learn about in the subsequent chapters. But at the concept level, what do we mean by linear growth and what do we mean by exponential growth? Any thoughts? Anybody? Dhanushri? Sorry. Srivatsab, any thoughts, any random thoughts? It could be as weird, as stupid as possible, that's fine. What is the basic difference between linear, when somebody says linear growth versus exponential growth? What would be your...
Linear growth is like constant.
Okay.
And exponential is like not constant.
Okay. At least you said something, right? That makes me happy. Let's see, anybody else in the class? Yadev.
Just adding on, linear is like the y value is increasing at a constant rate, where in exponential, the y value is increasing at an increasing rate.
Okay, increasing or decreasing rate. Yeah, Chris. Chris, you
I was gonna say pretty much a similar thing, but it's like as it starts off increasing less, but then it exponentially keeps growing. So it could start by growing by a little bit, and then it'll keep growing by a lot more.
Okay. So now I'll give you guys one silver bullet that will help you relate it in a much easier way. And again, linear growth, exponential growth, all that we will talk about when we talk about, again, we'll come back to the polynomial functions, the system of equations and whatnot. And that is where we'll be able to relate it again. But in the simplest of form, linear. Okay. Now when we're talking about growth, essentially what growth means is when one value changes against another one. Okay. Meaning growth of y against every increase of x. That's what is growth. Yeah. Or how much y changes for every change in x. Now when you say linear growth, you are essentially talking about a linear equation. Because y is growing in a more linear way. Y is growing against x such that it frames a line, straight line. Now, so when you're talking about a linear growth, you're talking about this kind of a form where y increases for every increase by a certain value. Now when you're talking about exponential growth, when you have power 1, that is linear. When you have x to the power something which is not 1 or near 0, that is when things behave more erratic, more exponential. It could go like this, or it could go like this, or it could go like this. Yeah?
Hi sir, sorry.
Yes, Ami. No problem, beta. You have to just wait for 2-3 more minutes and then we'll start your class.
Okay sir.
Alright? So,
Yeah.
yeah.
Sorry.
Yep. So when you talk about linear growth or exponential growth, the simple thing is when y is growing in a more linear, more predictable form, or this relationship between x and y can be represented as a linear equation. That's when we are talking about linear growth. When my x and y is changing in a more erratic way, where it is not forming a linear equation, it's forming a polynomial with a power to the x as more than 1, or even things like this. It will result into a polynomial function. It will give you a more erratic behavior where you are multiplying, you are not adding. Here you are more multiplying the same thing. Okay, that's where we talk about the growth being exponential, because see, look at this, you have exponents other than 0 and 1 to the x. That's why the graph it will plot, the growth it will demonstrate, that will be more exponential in nature. Yeah. So with that being said, I'll take a pause, and this marks the end of unit 2 for you guys. My request to you all would be, go to the Khan Academy, finish all the unit tests for this unit, and see if there is even a simplest of the possibility where you are getting stuck. And if you get stuck, that will make me happy, because I'll have something more to teach. If you don't, that will make me happier. Yeah? Alright. So I'll let you guys go.